Today we are happy to have for our speaker Kang-Kuen Ni from JQI West. Kang-Kuen got her PhD at JILA, working with Debbie Jin, and she was part of some of the phenomenal results of making nearly degenerate polar molecule gases. Graduated in 2009. She was the winner of the 2010 AMO Thesis Prize from the APS. And she moved from JILA out to Jeff Kimball's group at Caltech, where she had a postdoctoral fellowship. There she changed what she was doing a little bit and got involved in optomechanics and had a very nice result of improving optomechanics using optical springs rather than mechanical springs. And recently she returned back to JILA, and she's now working with Eric Cornell on an experiment looking for an electric dipole moment. This is, I think, Eric's great white whale experiment. He's been working on it for... So I'm impressed that he decided to do this. But how long has Eric been working on it?
Actually, that project started at the same time that we started the KRB experiment, which is 9.5 years ago.
9.5 years ago, yeah, right. So she's got a lot of courage. Anyway, so we're happy to have Kang-Kuen today, who's going to talk to us about new prospects in cold molecular physics.
Thank you. It is a pleasure for me to be here today at JILA East. It's a pleasure to be here at JQI and give a seminar. And to tell you a little bit about my research and my perspective on some of the new direction of cold molecular physics. I certainly won't be able to cover everything and all the directions that people are involved with, but I'd like to give you just a flavor. People in this research area are taking on directions such as quantum computing, precision measurements, ultra-cold quantum chemistry, and study of exotic quantum phase and matters. And the basis for this many new direction is really because molecular samples can now be prepared cold, and its internal and external degrees of freedom can be controlled precisely. This has greatly evolved since the early days of molecular spectroscopy. Molecular spectroscopy was traditionally a study of molecular structure. Molecules are much more complex systems compared to atoms. For example, molecules has additional rotational degrees of freedom or vibrational degrees of freedom. So it was sort of very early on that we know that the molecules are complex, but we're interested in sort of testing our knowledge of quantum mechanics by applying first principle calculation to see if we can understand molecular structure. Okay, so here is an example of very complicated spectra from our laboratory. If you were to zoom in, say that region, you will see that actually all the lines are actually accounted for. Here are rotational transition involving also electronics transition with changing of rotational quantum numbers. But the message here is that we pretty much understand what is going on here. Okay, so perhaps it's a good time to discuss a little more about molecular structure. Here I plotted out energy versus internuclear separation. I'm considering here diatomic molecule. So only atoms, a molecule consists of 2 atoms. Okay, so on this energy scales, there is actually a variety of different energy transition. For example, the biggest one will be the electronic transition. Because I'm using the language of cold, I put sort of the equivalent temperature for the transition on there as well. So electron transition is 10,000 Kelvin equivalently. If you look further down, then there are the vibrational levels, which basically follows the simple harmonic oscillator spacing. And they're spacing roughly on the order of 100 Kelvin. Furthermore, rotational level, which follows angular momentum Schrodinger equation, and their spacing goes like that. And one more levels down, you will be the hyperfine level, which is on the order of equivalently 100 microkelvin. Okay, so the structure of an atom and molecules are like the fingerprints of the atom and molecules. And that has been an extremely useful tool for, say, astronomical observation. Here, astronomers looking at outer space, looking at supernova, galaxy, and astronomical objects, they can disperse the light through a prism and look at the, for example, knowing the composition of those astronomical objects. When they compare the spectrum, they see the lines compared to the laboratory result, and they in general found that the lines are redshifted, which means the objects are moving at a velocity and predominantly away from us. They can plot velocity versus distance, and they realize that this is a clue to show that the universe is expanding. Okay, so astronomical spectroscopy continues to be important tools for astronomical observation, including sort of most recently figuring out that this expansion rate is actually the universe expansion is accelerating. Knowing the absorption lines of a molecule precisely has also led to the first atomic clock. Here's an excerpt from Popular Mechanics, 1949. So here I just read you some of the highlights. This clock was so accurate that it will lose only 1 second in 300 years. Okay, and the clock consists of a quartz crystal that through a large chance of electronics is constantly being compared to the vibration of ammonia molecule, which here Dr. Kang-Kuen, who was the director of NIST, actually at National Bureau of Standards at the time, is holding this model of ammonia. This quartz crystal is constantly compared to the ammonia molecule, turning itself inside out at a rate of 24 billion times a second. Certainly by today's standard, this atomic clock is not accurate at all. The most accurate atomic clock nowadays keeps time without losing a second at 3.7 billion years. But certainly it was the first sort of, they call it the first clock that is not based on sort of astronomical motion. Some of the developments or the motivation from improving the atomic clock has certainly led to a whole explosion of the field of atomic molecular physics, including the invention of the laser cooling. So the ability to be able to cool and trap molecules and be able to have the system such that the molecules can be interact for a long time, and the experimenter can probe with a variety of experimental knobs has allowed us to do a variety of experiments. I would like to discuss with you 2 experiments that I've been involved with, namely precision measurement experiment and ultra-cold quantum chemistry. And hopefully in the future we can move toward also the direction of study exotic quantum-based matter. Just to turn the pictures into words, precisely I will be telling you a search of an electron-electric dipole moment in molecular ions, why it's interesting and what we have done so far. And a second example where we can prepare molecules translationally cold as well as controlling every single internal degrees of freedom. We can make molecules at 200 nanokelvin, and quite surprisingly, seeing ultra-cold chemistry. Okay, so first, the search of electron-electric dipole moment. This is work done, currently being carried out in Eric Cornell's group, and Eric Cornell and Jean's group. Okay, so let's meet Miss Electron. Miss Electron, we know it has a charge. We know its mass really well. It has the spin h bar over 2, and associated with the spin there is a magnetic dipole moment. So when you turn on a magnetic field, it's going to orient itself. What about an electron-electric dipole moment? Okay, so if the electron were to have electric dipole moment, it would look like this, where the charge is distributed a little bit, non-uniformly. And what this would actually looks like is as if the center of the charge, which is sort of this ball of charge, with the center being here, is displaced from the center of mass. People for the last 4 and 5 decades has been looking for this displacement and put the most stringent current experimental limit to be that distance being less than 10 to the minus 27 centimeters. So it's extremely small. How small is it? That's compared to some size that we can comprehend. For example, a typical size of an atom would be a Bohr 5 times 10 to the minus 9 centimeter. So much bigger than what we're looking for. Even Large Hadron Collider colliding at its highest energy is equivalent of probing a length scale of 10 to the minus 17 centimeters. So we're 10 orders of magnitude smaller than that, the current limit being 10 to the minus 27. In JILA, as well as many other places, we want to push this number further, and we aim to improve this number by another 2 orders of magnitude. Okay, so what's the significance of an electron having an electric dipole moment? Physicists like symmetries. We like to see symmetry breaking even more. Here is an example. If the electron has an electric dipole moment, it will look like that, where there's a little spin pointing one way and a dipole moment showing up as the displacement. Okay, so if we were to do a parity transformation, parity is violated because the dipole moment changed direction, not the spin. So they look differently under the parity transformation. But maybe not so trivially will be the time reversal symmetry being violated, where the spin changed direction but not the dipole moment. So time violation is shown up here. So far, we think the CPT, charge parity time, together is a good invariance. At least there's no evidence for that to be violated, and that is actually also in the standard model. It would, because of the T violation, it would imply that CP is violated. So in the standard model, there are mechanisms of CP violation, and from there, you can get an idea what you would predict what the electron-electric dipole moment to be. And for that is predicted to be extremely small, 10 to the minus 38 e centimeter. However, there are physics beyond the standard model, such as the supersymmetry, as well as others, that are predicting a much bigger electron-electric dipole moment at a level, say, 10 to the minus 26 or smaller. So already the current best experiments have already carved into the length where they can put stringent constraint on physics beyond the standard model. As an experimenter, the exciting thing is really that if we were to see something, we know it's because of the small background of the standard model that we're seeing new physics. And even if we don't see something, we can constrain theories that are already in the range which a lot of people are believing to have some truth to it. So our experiment looked kind of like this. We have our vacuum chamber back there, and the rest of the things that you see are all lasers, or things that are involved with stabilizing lasers and stuff. Okay, so we know the measurement of an electron-electric dipole moment would be significant, but how do we measure in the laboratory? First, you may know how we can measure the magnetic dipole moment. In the presence of a magnetic field, we have an electron pointing one way, and we can shine radio frequency photon such that we can flip the spin. The probability of flipping the spin as a function of frequency shows up as this little Lorentzian, where the peak is centered at the dipole moment times the magnetic field implied. So that's how we measure the magnetic dipole moment. To measure the electric electric dipole moment, we can turn on the electric field. Then we'll see that the line shifted one way, and we can reverse the direction and see the energy shift the other way. And the difference is really just the 2 times the electric dipole moment of the electron times the electric field. So that's what we would like to do to measure. To make a really good measurement, the figure of merit would be that if we can have this electric field as large as possible. So then we have a very big, we have this really big electric field trying to separate this 2 different direction resonance as large as possible. Also, we want to have a very large coherence time because that way we can have a very, very narrow resonance. Finally, we need to have this peak as high as possible, actually large signal to noise, which means we need very large number of counts. So together, we have a figure of merit of effective electric field times the coherence time times the square root of the number, effective number. I should say that this is what the figure of merit would be for evaluating statistically. What ultimately will limit you will be the systematic error. So for that, the long coherence time is very important because that narrows down your lines, and you can tell the center of that much better if you have a very narrow line. Okay, so we know how we can measure it. We can quickly put on a large electric field on the electron, but the big problem there is that the electron will just quickly accelerate it away to your electrode, and you don't have very long time to probe this energy difference. Okay, so how do we go about that? Already in the 1960s, Pat Sanders came up with a solution that is to attach the electron spin to a big atomic nucleus. And through relativistic effect, that not only you apply electric field to a neutral species that doesn't, that won't just accelerate away, but rather that you actually get an enhancement of what you apply in the laboratory by a factor of z, the atomic number, to the power of third. So that's the effective electric field that the electron is going to experience. So for 4 and 5 decades, people have been perfecting that type of experiment. Eugene Cummins at Berkeley, using a thallium beam, which is a very heavy atoms, can improve this, really perfect the experiment to high degrees of perfection, where the effective electric field is very large, so it has a very large enhancement factor on the order of 500 or so. He built a very long beam, so it has a reasonably long coherence time, 2 milliseconds, and have a large flux. So together, he has a number of this dipole moment constraint down to below 1.6 times 10 to the minus 27. So how can we possibly top that? Usually, looking at this figure of merit, you will try to improve one thing by a lot, and while not sacrifice the other two to be able to make a better measurement. For us, we want to use molecules, because molecule can get the electron inside the molecule can experience much larger effective electric field than you can do with either in a laboratory or with atoms. So we can apply something like 10 volts per centimeter, hardly anything, and the effective electric field inside the molecule for the electron would be 3 orders of magnitude bigger from what you get with atoms, so 10 to the 10. So 10 gigavolts per centimeter. Secondly, we would like to trap our molecules. So for that, we want to use ions so that we can probe for a long time and not having a being where the transient time is what is going to limit you. So we trap our molecules in this ion trap. Okay, so in the figure of merit, we hope to improve the effective electric field by 3 orders of magnitude. Also, the coherence time by 3 orders of magnitude. Our number is going to be much less because we're working with ions and molecules, but together we think we can improve this number by 2 orders of magnitude. Okay, so what molecular ion to use? I wanted to argue that because we're choosing molecules, we have a whole host of possibility. We would like to actually design our dream molecule. So we write down a list of criteria that we want. We want to have a very large effective electric field, which means we want to have this unpaired electron, which is orbiting in the s orbital, so spherical, so it can constantly having this strong relativistic effect near the heavy atom. We want to be able to polarize our molecule in the laboratory frame easily, which means the opposite parity state has to be very, very small. So for that, we want this is kind of a technical jargon, we want to have lambda doubling, which means we want an electron that has a d orbital. For a lot of this type of experiments, systematic, especially magnetic dipole moment mimicking the effect of an electric dipole moment has kind of set the limitation. So we want to have a system where it's very insensitive to magnetic field. So we want to have a molecule that has a very small magnetic dipole moment to reduce systematic error. And for that, we choose a triple delta 1 state. This is just a very special electronic state. You should just think of that where the electron orbital magnetic moment cancel the spin magnetic moment, such that you basically get a factor, roughly a factor of 100 less than the Bohr magneton. Finally, you want this particular electronic state to be long-lived, so then you have a not only you can trap them for a long time, you have a very long time to probe its states. So you want this state to be either the ground state or low-lying metastable state. Okay, so we look, well, not me personally, but they look in the periodic table and figure out that the choices that we're pursuing right now is actually in parallel is hafnium fluoride plus and thorium fluoride plus. Okay, so I would like to tell you now we have chosen our molecules. A lot of the time has been spent on trying to figure out how to manipulate molecule internal state and how to detect it. So that's what I'll be telling you about. The challenges there was that we're working with molecule. It's very hard because, first of all, where are the states? Second of all, how do we make them in a single internal quantum state, or as much in a single internal quantum state as we can to make our measurement? For example, here is kind of a quick schematic of experiment. We use supersonic beam, so we have relatively cold on the translational temperature, or not, this is center mass, but rotational temperature on the order of tens of Kelvin energy. So we have a beam of molecules, even at the rotational temperature of 10 Kelvin, if you include all isotope, all parity, all angular momentum quantum number and rotational state, it will mean that only one molecules out of 300 will be in the right state where you want to make your measurement. So that's obviously not a very good starting point. So how do we go about improving that? And finally, even if you can create a molecule in that particular state, how do you actually know it is in that state? So efficient detection of ion or molecular ion in a single state is also very challenging. Okay, so we can improve our initial condition by a technique of auto-ionization, state-selected auto-ionization. So what we do is we start with hafnium fluoride neutral. So we start with neutral molecules. We drive a 2-photon transition. I'll tell you more about the first photon in a second. The second photon drive up to some kind of rebirth state where the electron is highly excited, and it will just quickly sort of goes away, and what you left with will be a hafnium fluoride plus ion. Okay, so this rebirth state is chosen for two reasons. One is that the energy itself is just barely above the ground state, the vibrational ground and the electronic ground state of this ion. So energetically, it can only fall down to the vibrational and electronic ground state. However, the rotational state is not managed so far. That is done by choosing this first transition such that it only talks to certain rotational state of the neutral, and then going to a rebirth state that has a particular angular momentum. So for that, when the electron flies out, what you're left with is somewhat of a selective rotational quantum number. So for that, we can create 60% of our molecule in a single rotation, vibration, and electronic ground state, actually not ground state, just a single state, but half of that will be in a single J and NJ. So for that, we have improved our initial condition by a factor of 100 compared to if you don't do anything. However, our molecules are now in the singlet sigma plus. It's not yet in the triple delta 1 state, which is where we have chosen very carefully to improve, to have very little systematic and to have a large effective electric field to do our measurement. So we still had to bring our population to the triple delta 1 state. And for that, we use the 2-photon coherent transfer technique. Okay, so this, actually, I'm going to spend a lot more time because this very similar type of technique you will show on the second example that I will tell you. So here, we have a 3-level system, 3 molecular levels. We start from, just consider it as the red and the blue and the yellow state. And the 3 levels, ideally we want just to transfer population from red to blue, but there's very little coupling. So for that, we want to go through an excited intermediate state. And to do that, we use 2 lasers that are very different in wavelength, 100 nanometer, roughly 100 nanometer difference in wavelength, but it has significant dipole moment. So this system is very similar to, say, pendulum and springs. So you can think of the pendulum as the states and the spring as the laser that couples the 3-level system. So once it's coupled, I'm free to tune sort of the length of this pendulum until it's on resonance with this, where population can go from here to there. So just a classical analogy, you can think of all the population is here, and I tune this 3rd level coming through resonance by changing the length of this pendulum, and the motion from here all get transferred over there. Perhaps more atomic physics language, we can consider this as in the dress state pictures. So because all the levels are reasonably large to tune from the yellow state, so it's just kind of sitting up there. But down here, we have the state of both the laser and the red and the blue coupled together. So down here, we have a state, well, we have 2 states that are both mixtures of the red state and the blue state. And as a function of little delta, which is the laser frequency difference, energy difference between these 2 lasers versus the energy difference between the red and the blue. Okay, so that's the little delta, and as we sweep the little delta, we can bring population adiabatically from red to blue. And kind of a technical thing, I think the atomic physicists will appreciate this. And because we have a gas that has very large Doppler width, because we're working with temperature of 20 Kelvin or so, this little delta is actually sweeping by the motion of the ion in the trap itself. So we fix the laser, and as the ions are moving in the trap, it's experienced different Doppler with different Doppler shifts. So it's basically moving this little delta and it crosses 0 when it sort of goes to the side of the trap and come back down. So this is actually basically done using that technique, that implementation. One thing that didn't capture in the sort of the pendulum and the spring analogy is that for this to work, this two laser has to have a well-defined beat shown as here. Well, you can't really do this because they are really 100 nanometer apart in wavelength. So for that, for the first time, we can now actually put population in a triple delta 1 state. So here I show you actually feature in there. There are actually hyperfine states of the particular vibrational and rotational states. Okay, so now we can populate our molecule in the state that we would like to do our measurement. The first thing that we want to do is to turn on our electric field.
Well,
And we have
I guess I'm confused by your explanation, because as you said, you're relying on the thermal motion to isolate the state you want. So in this picture you just showed us, how do I know that that's the state I want?
Right. So the exact implementation is really tuning this low delta. I guess so. We have two states. They are coupled by this frequency exactly. So that already gives you the frequency selectivity. But to really go for population from red to blue, we need to adiabatically transfer, which means we change this lower delta, and that is the exact implementation is just that the ions is moving in a trap, and we can let it go for half a period, so then it actually switch itself from this internal state to this internal state because of the presence of the laser. So that gives you the selectivity.
So then you turn off the light after a certain
Right. So turn on the light after half a cycle.
So it's one clarification. So when you've done that, you caught just the ones that had the right micromotion. Everything else is left behind.
So that's
You don't do everything. You just do those that have the right micromotion.
right. So it's actually not micromotion because the micromotion is in the plane while our laser is coming this direction. So this is just purely the harmonic trap frequency that you should consider. But in principle, because they can all start out, basically they can start out different velocities. So they can start out here or they can start out here.
Yeah.
But at least in terms of half a cycle, they should only cross the 0 once, unless they're already near the 0. Yeah. But I mean, in reality, we actually leave it for longer to have roughly a 50-50. We actually transfer roughly 50 because we're still sorting out of the Rabi frequency problem, but that's the general idea.
So effectively, you only capture roughly half of it.
Right. So we transfer 50% right now.
And then you take the others out.
No, they're still ion, they're trapped, but we don't see them. I'll tell you a bit more about detection. So, okay, so now we have populated our molecules in the states that we want to do our measurements. We need to turn on the electric field, and because we're working with ions, our electric field has to be rotating so that the ion doesn't just accelerate to your electron and get lost. So that rotation frequency has to be relatively fast, and for us it's the fastest frequency in the system for 250 kilohertz. Certainly not fast for ion trapping experiment in general, but for us it's the fastest. So I show you two peaks in the past, in the last slides, and now each peak depends on their exact quantum number. It's divided into either 2 or 4 because of the stark shift. And you can see that our electric field is very, very mild, 8 volts per centimeter. And already we can polarize our molecule in the laboratory. Okay, so I kind of rely on you believing me that when I say the state of the molecule is in, and it is in that state, and we actually spend quite some time figuring out how to actually determine that, and finally came up with a technique of photo dissociation, state-sensitive photo dissociation. Okay, so say I'm preparing my molecule in the triple delta.
Sorry to interrupt you, but that's destructive, is that it? You
Yes,
know that
it is
you know that it
refracted.
was what you
Right,
thought.
Right, exactly.
Okay.
Yeah. So we start with molecule in a particular rotation vibrational state of triple delta 1. We can shine a laser, which this laser will tell us which state it is in. So it's a state-sensitive transition. And then we have another laser which bring us up to a repulsive curve where we break hafnium fluoride plus into hafnium plus and fluoride neutral. Okay, ion counting is in general very efficient. So this way we can count the hafnium plus that came from this dissociation process and know that they were actually in the state that we started out with. So in this picture, this is our chamber. We have 6 electrodes there. We have our hafnium fluoride plus trapped in there, and we shine the 2 laser. As we break it apart or not, they get kicked to the ion detector, and through the time of flight, sort of the time it takes to arrive at the detector, for example, hafnium, given its mass, it's arriving at 35 microseconds after we kick it. Because hafnium plus is 10% lighter, it will show up earlier. So this way we know these are the ions that came from that particular state that we dissociated. With this technique, we can measure, for example, the lifetime of triple delta 1 state, which is on the order of 2 seconds. There could be still some technical limitation to it, so that's why it's preliminary. But already this time scale is very, very long, and we certainly do not expect that our coherence time is going to be limited by the lifetime of the molecule in this particular state. I wanted to also say that there are competing experiments using, again, triple delta 1 as the state for neutral molecule to search for electron-electric dipole moment. And for them, the lifetime is on the order of 2 milliseconds. So we're 1,000 times longer. Okay, so just a brief conclusion so far. I've told you about this electron-electric dipole moment search as a sensitive tool for physics beyond the standard model. Molecules are really nature's high electric field laboratory that allow us hopefully to make this very, very sensitive measurements. In JILA, we have mostly been working with trying to figure out ways to manipulate the internal states of the molecule and to detect it. And we're also turning on the magnetic field now to be able to start our precision measurement on the electron-electric dipole. Okay, so now I wanted to tell you a second experiment which you may have heard of. And some of you have worked on it as well, on the experiment where we can make polar molecules at very, very cold temperature. This was work done in the group of Debbie Jin and Jing Yi with collaboration with certainly a few of you in this. Okay, so the motivation for this work was really coming from the success of ultra-cold gas atoms. For example, bosons and condensate or degenerate Fermi gas are really examples where you control the external degrees of freedom of the neutral atoms to high perfection. And this type of systems, temperature on the order of less than a microkelvin, in recent years really has been sort of the focus being on using this type of system to study strongly correlated systems, such as superfluidity in Fermi gases and quantum phase transition in optical lattices, and more. The reason this systems are so ideal is that in general the microscopic interaction of the atoms really plays out to give you the macroscopic behavior of the gas. So for atom, that's in general short range, has contact interaction short range, and isotropic. For polar molecules, you will have the addition of dipole-dipole interaction, strong dipole-dipole interaction, which is anisotropic, so it can be repulsive or attractive. It's long range, 1 over r cubed, and the dipoles are tunable with an external electric field. Moreover, molecules have complex internal structures that allow you to have new ways and new degrees of freedom of controlling. For example, the rotational state you can control with microwave. Before we started out, and even currently, there's ways of pursuing a co-gas of polar molecule. Certainly, this is not the most updated, but sort of before our work, there are in general 2 different ways, and where there's the sort of the criteria or the figure of merit to tell you how cold or how dense the gas is by the phase space density, and that is on the order of 10 to the minus 13 to 10 to the minus 15. And for the onset of quantum degeneracy, that number will be on the order of 1. Okay, so the 2 different type of approach will be to start with molecules, which come in a jar or something, and come up with a clever way, usually kinematic ways to cool it, and that you get 2 millikelvin type of temperature. Alternatively, you can start with laser cool atoms and to shine light to bind them and make some molecule. You can get reasonably cold, but there's quite sparse. So we also start from ultra cold gas we also start from cold gas of atoms, but in particular near quantum degenerate gas, not just laser cool. So we start from near quantum degenerate gas of rubidium and potassium. They are boson and fermions. The challenge there was that we need to, basically if you have just potassium, rubidium, and a cold temperature as atoms, they have to release on the order of 7,000 Kelvin worth of energy to bind together down to the vibrational ground state. So to efficiently convert atoms into molecule while staying cold is the challenge. So to solve that problem, we do 2 steps. First, we just make some molecules. We make weakly bound molecule by preparing the gas really cold and ramping the magnetic field through a scattering resonance. This is the so-called Farnow-Feshbach resonance. So for this, we changed the size of the problem from 10,000 Borg, which is the typical interparticle spacing, to weakly bound molecule where their size is 300 Borg. You should really think of this molecule in a well-defined quantum state. It has a highly excited vibrational level, but it has a very specific angular momentum quantum number and vibrational quantum number. For these molecules, we can image them directly. We trap them in an optical trap. We can release them and take an absorption image for various times, so a millisecond up to 9 milliseconds or more. We can directly get information of the number and the temperature of the gas. Okay, however, we can make some weakly bound molecule. They're not polar yet. So to make polar molecule, you need them to be tightly bound so that the electrons are actually sharing between the 2 nuclei. Okay, so we still need to make tightly bound molecule, so then they're polar, and this 6,000 Kelvin worth of energy need to be carried away. And for that, we use light, and the laser light really carries away the binding energy. So we can shine light to this weakly bound molecule, make them highly electronics excited, but a tightly bound molecule. However, they would just quickly decay into a variety of rotation and vibrational states. Not only it will heat up a little bit, not very much, the binding energy is mostly carried away, but they will all go into a variety of final state, which is not what we want. So we replace the spontaneous decay with a laser, for that to make the process coherent, where there's no recoil heating and it goes to a single target state. For this to work, this two laser has to have a well-defined beam. Okay, again, you should think of this type of manipulation, again, very similar to the one that I've shown you previously, although the implementation is completely different. Okay, so actually going back to this picture, so we want to go from this red state to the blue state, and we really need to find this yellow state that has significant coupling that we can actually do this transfer. Otherwise, the springs are way too weak, and we can't really transfer population from here to there. Okay, so for that, we have chosen a state, doing some spectroscopy, chosen a state such that it has significant wave function overlap between something like 300 Bohr in size, as well as few Bohr of the tightly bound. Also, one non-trivial thing for the experimental implementation is that these two lasers, which are different in energy by 125 terahertz, has to have this well-defined B, and for that we lock the individual laser to a well-referenced frequency cone. Okay, so here is the data that showed that we were able to do that successfully. Again, you should think of the states here are the weakly bound molecule state, tightly bound low vibrational ground state, and we are constantly, we're monitoring, our imaging is sensitive to only the weakly bound states. So as we ramp the intensity to transfer our molecules from the weakly bound state to the rotational vibrational ground state, we see the disappearance of molecule from this state. To make sure that this disappearance is not just pure loss, but actually going to the state that we want the molecules to go to, we do a reverse sequence. So we see a majority of the molecules came back, assuming equal efficiency in the transfer. We have more than 80 and 90% of one-way transfer efficiency. Because this process is so fast, 4 microseconds, you should just think of this process as part of the imaging. So you can transfer molecule in the ground state, do the study that you want to do, and before you wanted to see it, quickly change its internal state and shine light.
So is this efficiency largely limited by the residual thermal motion of your molecules?
No, well, maybe a little bit too, but the molecules here are really, really cold, where the Doppler width is extremely small.
So what limits the efficiency? Because it should be 100%. If this was done well, is it spontaneous emission?
Right. So, yeah. So there's always that. So the way the exact implementation that we are doing is that the two. So that picture I show you is not very accurate, because it's in the exact implementation. You should really think of everything is on resonance here. Okay, so that's actually the true implementation that we have. So the red and the blue laser are on resonance to the excited state, but during this time we are creating a dark state, which only involves states of the weakly bound state and the vibrational ground state. So we hope to directly project to that to start and just evolve population from one to the other. And that projection is not perfect due to, say, the laser coherence and I mean, that also convolute with a little bit of the possibly a little bit about the Doppler width of the atoms and molecule. But it's all right. So it's all kind of convoluted. We're trying to do our best, but I think, yeah. I think at least when we first made it, we were surprised how efficient it was.
It's just the theorist who's not happy with 90%.
Okay, so for that we can make molecules at the phase space density of 0.1, so that's 11, 12 orders of magnitude improvement, and put them in single rotation, vibration, and electronic ground state. We can further manipulate its rotational state by microwave transition to be able to populate them in a single lowest nuclear spin state. Okay, so I have already said that. It's 11th order of magnitude improvement from previous result, and it's still the most, the highest phase space density polar molecule experiments. Okay, so at the beginning I told you about sort of all the different energy scale in the molecule. We have managed in all the scales here, find energy, get rid of it, and vibration, control, rotation, hyperfine, and end up with a translational temperature of a few hundred nanokelvin. Our trap is held at 5 microkelvin, that's the trap depth. So our molecules are happily living in the trap, not going away. Except for, is that really the case? Can they decay, and what actually happens? What determines it? We see our molecules are long-lived, on the order of seconds, but we also saw them going away as pairs. So this is a two-body decay of our molecules. What could possibly happen? They're already in the lowest internal state. When they can go away, they can probably, the only way they can go is to come up with becoming a different chemical species. It turns out there's only one possible exothermic reaction, not even 2 or 3 different ways, but only one, and that is 2 carb comes together and goes out as potassium dimer and rubidium dimers, and that energy access is on the order of 10 Kelvin. So small for a chemist, from the chemist's point of view, but it's very big from our point of view. However, the molecules that we're dealing with are spin polarized fermions. You would expect that the collision should really be suppressed at ultra low temperature. To illustrate this point, we can see here, so molecules, while we're dealing with spin polarized molecules, they don't really collide head on. They can collide with 1 unit of angular momentum. But that's just really just what we call the P-wave barrier. There is still probability for 2 molecules to tunnel through the P-wave barrier and get close enough to react in the short range. But you can see that it's more likely to tunnel through, say, this barrier of 24 microkelvin for KRB. If it's hot and if it's cold, then that probability is going to reduce. And for that, we can actually vary our temperature from 200 nanokelvin to a microkelvin. We see this linear dependence, which is what you would expect for this P-wave tunneling through the barrier. Okay, so here I show that this is a P-wave collision. If we have the possibility of manipulate that nuclear spin, so we can flip the spins of half of our molecules, and now they are distinguishable fermion into 2 different states. So now this P-wave barrier is removed. They can collide much fast. They can come together at a much faster time scale. This rate goes up by a factor of 10 to 100. And it's temperature independent. Because the consequence of they coming together is chemical reaction, it's really an example of a chemical reaction where the rate is determined by, it cares about the quantum statistics. Okay, so now I wanted to add another term in the long-range potential, namely actually turn on the electric dipole moment where the dipole-dipole interaction comes in. And this C3 over R3 actually depends on, the C3 actually can have different kind of signs. Depends on the orientation of the molecule comes together. So it can be attractive or repulsive. When it's repulsive, this P-wave barrier height is being raised while when it's attracted, the barrier height is being lowered. In our gas, we working with the gas that's free to move in all three directions. It's effectively having all three different channels going on. Okay, so what we saw was as a function of a dipole moment. So this is the regime where, for one, the attracted channel, the barrier is being lower. We see this rate increase, and that is really due to this barrier reduction due to the attracted dipole-dipole interaction. For small dipole moment, it's still the usual van der Waals interaction. And again, the rate of this can really explain by this simple formula, which is really just how the barrier height scales with the dipole moment. Okay, so in conclusion, I told you about the challenges for working with molecules. We have made progress. There's still progress to be made in cooling, trapping, and detection. And I'm only telling you a very special set of experiments. There are also other experiments like the star decelerator or evaporator cooling and things like some of the new developments. They're also very exciting, but here I show you some of the progress we made, and there's also progress that others have made in the field. Because of this, we are able to do cool things with them. For example, I've told you about a precision measurement experiment we're working on, and actually, to our surprise, the study of ultra-cold chemistry. In the future, we certainly want to still get colder. We want to trap them in a variety of configurations. We want to detect them at perhaps even the single molecule levels. And all those ingredients will be needed for study of novel quantum phases. Here, just to throw in an idea, some of the things that people have talked about for polar molecules, for example, molecule in a 2D optical lattice, you can prepare them with different kind of filling factor. You can prepare them in different type of non-insulator states, and perhaps at the right condition, because of the long-range interaction, at the right conditions, you can also get supersolid phases. For that, I'll just stop here, and thank you for your attention.